And let me also open the slides. So this is what we're doing today. What should I choose? So we're talking about making choices. And of course, we've been talking about making choices the whole term. But we're going to look sort of at, instead of looking at a general Markov decision process where there's sort of the value function and like what is the optimal action, and there's a lot of things going on. We're going to really simplify it down to a very simple problem and just talk about what's going on there. And it's already complicated enough that interesting things can happen. So what is the problem going to be? You can see the picture. There's this fisher person, and there's 4 lakes, A, B, C, D. And the only thing you got to decide is which lake you're going to go to. So you're going which lake you're going to choose from. So here's the mathematical assumptions. The fishing trip is going to be capital T days long. T is some integer. And you know what T is. You know it's a 10-day fishing trip or whatever. And we're going to look at the case where T is really large. So we're going to imagine T as some big number and try to think of, in terms of T as the big number. There's going to be L distinct lakes, L for lakes, and L is small. So in the example, we're doing L is 4. But you should think of, we're kind of doing the T goes to infinity limit and the L fixed limit. Let me give these to you as you walk in. You're going to need them. Okay, so every morning you wake up and you get to choose one lake to go fishing in for the day. You go fishing at that lake, and you catch some number of fish. And here's the thing. Every lake has a different probability distribution for the number of fish you will catch when you fish at that lake. So maybe some lakes have a lot of fish. You go there, you catch like 100 fish. Some lakes suck, there's like barely any fish. And you don't know what they are. You don't know what they are. So you have no prior knowledge about which lakes are good. You didn't read any like Yelp reviews of the lakes or anything like that. You just know nothing about the lakes. And this is an important point. The days of fishing are independent. So if you go fishing on Monday at Lake A and you go fishing on Tuesday at Lake A again, the 2 days are unrelated to each other except for they're from the same lake, right? So it's not like if you can't catch all the fish or something from a lake. It's not like it will ever run out of fish. The distribution on Tuesday is the same as the distribution on Monday, and they're 2 independent draws from the same random variable. If you were instead of being a fisherman, if you were a gamer, you might think of the lakes are like different dice, right? There's a 20-sided dice or a 8-sided dice, and you don't know how many sides are on the dice. But every time you roll it, it's an independent draw of that number. Okay. Last important point: you want to maximize the number of fish you can catch. So you're not just there for the lulz. You really want to catch a lot of fish, and you want to figure out where is the right place to go to catch fish. Questions or comments about the setup? Okay. So we can either play the game, or I can make some comments about why this is not a silly thing. But I think let's play the game because it's more fun. So let's start by playing the game, and I'll make the comments on why this is a real life problem later. So here's the game made by me, and you have 4 options. There's 4 lakes. So L is 4 and T is 40. We have 40 turns or days. Our score is the number of fish we've caught so far. When you start going to these lakes, we're going to press A, B, C, D. It's going to keep track of how many times we visited each lake, the average number of fish we've caught so far, and there's going to be a little list here with how many fish we caught. But those are the lakes. If you press 8 times 5, that's going fishing at Lake A 5 times in a row. And maybe I'll give you guys an option to vote for the times 5s as well. But you have your cards, A, B, C, D. And so just hold up which lake you want me to go fishing to, and I will press the corresponding button. All right. Let's see. Okay. Interestingly, everybody is either A or D. So B or C got absolutely no love, and we have 5 to 4. I think we have Lake D. Lake D. Okay, guys, we caught 10 fish at Lake D. So we visited Lake D once. We've caught 10 fish, and that's Lake D. All right, where do you want to go next? Hold up your card. Okay, we got quite a few people. We got 4 on Lake B. Let's Lake B. 7 fish on Lake B. We're up to 17 fish total. 38 days left. Where do you guys want to go next? Okay, I'm seeing a lot of C's. C. 5 fish in Lake C. We caught 5 fish in Lake C. Where to next? Okay, lots. Okay, so again, it's split A and D. I got 4 A's and I got 6 D's. We're going to Lake D again. So Lake D, the second time we only caught 7 fish. And now we've visited Lake D twice. Okay, where's that? Where to next? Okay, I'm seeing a lot of A. A lot of A. 8 fish. Okay, where to next? Okay, it's very split. I got 3 B's, 3 D's, 2 A's, 1 C, and 1 didn't vote. 3 A's. Okay, so now it's like a 3-way tie. Okay, let's have a final rundown between A and C. Vote for either A or C. If you were in the other ones, you gotta split. Okay, looks like A is taking lead. A is taking lead. Okay, A, we only caught 6 fish at Lake A. Where are you gonna go next? 3. D, lots of D's. Lake D, okay. Lake D, we caught 9 fish that day. Where to next? Okay, we got the little D voting block over here. Voting for D. Okay, we only caught 7 fish. Where to next? 2 D's, 3 D's, 4 D's. Okay, I think D wins again. D wins again. Okay, only 8 fish that time. Where to next? Okay, now C is winning. C, okay, C. C, we caught 6 fish on C. Where to next? I got 4 D's. 4 D's is winning it. Okay, we only caught 4 fish at Lake D over here, guys. All right, where to next? Okay, I got C's. 3 C's is winning? No, 3 C's and 3. Okay, you have to vote between C and D. It's a tie. Some people still have their B cards up. So C or D, guys?
Oh, C or D.
Oh, C.
I heard C or D, sorry.
D. Okay, 7 fish. Okay, where to next? Wow, it's very split. This is very interesting that you guys. Okay, B is winning by a slight majority here. B. Okay, 10 fish on Lake B. Okay, where to next? Oh, I'm seeing strong B vibes. Okay, less strong B vibes. 2 C's, 4 D's. Okay, D is winning it by a hair. Okay, where to next? All right, this is really interesting. 3 A's. A coming out of nowhere. Okay, A. All right, where to next? Okay, 3 A's, 3 C, 4 A's. Okay, A takes the lead again. Oh no, this is really exciting. Okay, what's up next? Okay, C is strong over there. C is strong. Okay, what's next? So you can just hold up the card anytime. I'm going to assume your vote is for the next button press. Okay, I got 4 D's. Yeah, 5 D's. Okay, D. All right. Next up. B. B is winning. Okay. Next up. B is still winning. Okay. Next up. Okay, strong B block over here. Okay. 12 fish on Lake B 2 days in a row. Okay. B. Okay. All right. You guys want to do a 5 times B? Put your B up really high if you want to do a 5 times B. Okay, let's do 5 times B. Okay. 5 times we got like a bunch. 5 times B again? You guys want to do 5 times B again? Okay. 5 times B again? Anybody for something other than 5 times B? A couple people want D. I think we're doing 5 times B. 5 times B. 2 days left. Which one do you want? B. Okay, we're doing. Okay, so here's our final fishing trip stats. We visited Lake A 4 times. We visited Lake B 24 times. Lake C 3 times. Lake D 9 times. And these were the fish we caught. And so on average, we caught like 7 fish a day at Lake A. A little less than 7 fish a day at Lake C, exactly 7 at Lake D. And Lake B had an average of 9.5 fish a day. And over here, it gives you some information. And it tells you the best lake was Lake B. So you guys got it right in the end. It turns out Lake B was the best lake. And the average advantage, 1, means Lake B, on average, you catch 1 extra fish a day at Lake B. So the lakes are pretty close together. B is a little bit better. And you guys somehow figured that out. Our final score, we caught 338 fish. Over here, it says AI score 343. 343. This is the number of fish. An AI had the same exact problem as you, same exact number of fish per day. They caught 343 fish. And what did they do? They did 4:28.26. You guys did 4:24.39. So the AI sort of won by going to Lake B 4 more days than you guys did. So what happened? I think you guys as a group, collectively came up with the right kind of strategy. Does anyone want to say like very roughly what the strategy was, or maybe questions or comments? Yeah.
Oh, I was gonna say my strategy originally was to iterate each one like twice.
Okay.
And see what the highest average was.
Uh-huh.
And keep picking the one with the highest average.
So
if the average starts going down like it did for D, you would switch to the next highest average.
okay.
And see if the number was going up. Or
Yeah. So definitely, I think at the end we were all, except for a few people trying to sow dissent, we were all convinced like we should just go Lake B. Lake B seems a lot better, and that turned out that was right. So kind of near the end of the game, we knew that Lake B had a higher average than the other lakes. We had tried the other lakes a few times, and we were like pretty confident Lake B was the best, and we kind of like spent a lot of time fishing at Lake B, and that seemed to work well. Like it was the right call here. But what else kind of went into the strategy? How else did you guys make your picks? Yeah.
I don't know if it's the right view, but what I was doing was, I was trying to like do a few until I got to make all of them around the same average, because I noticed they were really similar.
Uh-huh.
Once one spiked up, I'm like, okay, I'll just invest in that one.
Okay, so you waited until one was a lot higher than the others.
Yeah.
Did you sometimes vote for one that even though it didn't have the highest number, did you sometimes vote for it just because it was around the same value? Or did you always vote for the biggest one?
I voted for, so I saw that we were getting around 7 in all of them,
Mhm.
so I wanted to give them a few times to see if they actually were all the same. And
Okay.
whatever one would be the biggest, choose that one.
So for example, like Lake D would have 7 and Lake C would have 6.67. Would you do another round of Lake C or not? Would you be like, that's close? You would do another one just to check and make sure it's not actually. Okay? Yeah.
When I was doing it, I always just went one each, and then from there, I just went for the highest average each time.
So you did one each and then the highest average. Okay. Anyone else have that's a very simple strategy. But I mean, it combines everything other people have been saying into a simple thing. Yeah.
I want to say, like, just in terms of, like, there are things you can do in this game, like, already you can tell that you're losing turns, but you're making more educated guesses based on
Right.
the turns that you're losing.
Yeah. So there is some element of like a turn isn't just a chance to get fish. A turn is also a chance to get information, right?
Like Matt said, you would pick, like, the one that's the highest until it started to go down or it started to go up, but that's, like, you technically picking the least optimal choice.
Right.
To maximize your rewards.
Yeah. So I think this is a really great way to say the two things going on in this problem. And even though the problem I said you want to catch the most fish, actually when you're playing it, you have to balance two things. So it's not just catch the most fish. You're just trying to like maximize something. You're trying to balance two things. And one thing is how much fish you catch. The other thing is what she said. But is there like a word you would use to describe this other thing? What are you trying to do? Explore, yeah. So people say you're balancing fish versus exploring. That's how you would say it. Of course, most people don't do this with fishing. So what people call it is they say balancing exploring with exploiting. Exploiting is when you know a certain lake gives you a lot of fish and you just go there over and over again, right? And exploring is let's try all the lakes, even if we know we haven't had good results at that lake. Let's try it anyway, and that way maybe we learn that it's actually better. And I think you guys actually intuitively had a good sense of what's going on here. Like at the beginning, you did a lot of exploring, and at the end, you did some exploiting, and that makes perfect sense. When there's not many days left, if there's only one day left, there's no reason to explore, right? So the fewer days that are left, the more you want to exploit, and the earlier on in the game, the more you want to exploit. So that's what we're doing today. We're doing explore versus exploit, and we're trying to find good strategies to balance these two things. Any questions or comments about the game? Okay, so, here's the question. We've been doing this whole term. Does this remind you of anything we've done in the course so far? So I have a couple examples of why this thing matters in real life and not just for your fishing trip. But does anyone want to take a stab on what does this have to do with the course? Yeah.
Epsilon greedy.
Yeah. So what was Epsilon greedy doing?
5% of the time we would choose the randomly, and then 95% of the time we would choose the best option.
So in the course we had this Epsilon greedy algorithm, and Epsilon greedy said you have an estimate for the values of things, but don't always pick the best one. Have a fixed value of epsilon and try a random value on epsilon fraction of the time. And you could use the epsilon greedy algorithm to do this, right? So you could say, I'm always going to pick the one that is the best, except for 5% of the time, I'm going to pick one at random. And if you do that 5% of the time that you pick one on random will give you some exploring. And hopefully, you won't get locked in to something that is suboptimal because of this exploring. Yeah, so the danger of going pure greedy is if you go pure greedy, maybe by chance, the day one at Lake D is the best one, and then you miss out on all the gains from going to Lake B over and over again because you got sucked into going to Lake D because of one good fishing trip at Lake D. So the epsilon greedy, which tries all of them a little bit, is supposed to kind of balance that. So we saw that already, and we saw you needed that for certain algorithms in the course. And so what we're learning today is basically fancy versions of epsilon greedy. Can you replace epsilon greedy with something a little bit more mathematically smart? Are there some ways to say that how you should choose the epsilons? So you could make them always 5%. In some of my code, they've gone down over time. Can we justify any of those choices mathematically? That's really what we're doing today. That's how it connects to everything else. Any other questions or comments, ideas? So yeah, if you want, you can use some of these ideas in your final project. Of course, you can also just let epsilon equal 5%. It's up to you. Yeah?
How does the AI play?
Okay. So the AI plays, I'm going to explain to you by the end of maybe this class, maybe next class. We're going to get to how the AI plays. And we're going to learn an algorithm that is like a fancy version of the epsilon greedy that the AI does. And it's actually, it's fancy, but it's really easy to implement. So there's some formula. The AI has some formula, and it picks the maximum of that formula. So, and the formula isn't just greedy. It's not just pick the one with the highest average. It's something a little bit smarter than pick the one with the highest average. And that simple formula will balance being greedy, exploiting, with exploring, sort of in some sense, the optimal way. We're going to see what that is. Okay, yeah, that's a great question. So you can see that the AI kind of is actually pretty similar to what you guys did. So it kind of like does some exploring around, and then it kind of locks in on one and goes with that one. Okay, so yeah, that's definitely the relationship in this course. Yeah?
Before we get like super into what the AI is doing, does it have like can it accidentally use its strategy and like sink all of its guesses into the wrong?
Yeah, absolutely. Yeah, of course. Yeah. So there's no matter what strategy you do, there's a chance you can sort of get unlucky and go to the wrong lake over and over again. And I guess actually, I think when you play this, depending on how aggressive you play, you probably happen to see like 1 out of 5 times. So we kind of got, we found the best one in the end, but you don't always do that. If you want to try it on your own, so there's a friend of mine who's really obsessed with games. So he's a pro poker player, or he was. But so I made this game for a talk I was giving, and I sent it to him, and he started playing it like over and over again. And he played it I think he's played it more than anybody else. Like he knows all the strategies, and he got really good at it. And I think he was telling me that he finds the best arm like 5 out of 6 times or something, which he was proud of. Okay. Has anybody asked there's an obvious question here. Why is it called an arm? Did anyone notice that? We just called it the best arm. I never explained why. Okay, I'll explain why in a minute. You'll see why it's called an arm. Okay, so let's go back to the slides. So the reason related to what we've done in the course already is to, when you are doing algorithms that try to find the best value or the best choices, if you always go greedy, you sort of miss out on checking other values. So we want this balance between exploring and exploiting, and it comes up in these learning algorithms. Here's another example, which I call A/B testing. Suppose you have a bunch of versions of things, and you want to know which version is the most effective. That's a classical problem. And here's a great example that I really like that Netflix does. So Netflix will make many thumbnails of the same show. So here are 9 thumbnails for the same show, Stranger Things. And Netflix wants you to click on them. So Netflix shows you a thumbnail, and maybe some of them are really, really amazing, and like, oh, I really want to click on that. And the other ones are boring, and we don't want to click on them. And we don't know which is which. So how does Netflix decide, out of the millions of customers that visit Netflix, how does it decide which thumbnail to show people? Right? That's the question. And it does, basically, you can treat this problem like the lake fishing problem. So what are the analogies between how is this like the lake fishing problem? Well, in fishing, you go fishing for T days, and every time you make a choice. In the Netflix problem, you have T customers, and they visit your website, and you have to decide what thumbnail to show them. So the L lakes are like the L thumbnails. You can imagine this is the problem with 9 lakes, and you show them you make a choice on what thumbnail to show them, and then if they click on it, that's like catching 1 fish. And if they don't click on it, that's like catching 0 fish, right? And you would like to find the thumbnail that shows that has the most fish, the most number of clicks. So this problem is just like the fishing problem, but it's maybe in a more real-life context. And Netflix really does this. I think it's really cool. And in fact, Netflix, it's even smarter than that. Not only does it do this, it knows information about you based on what you've clicked on in the past, and uses that to further figure this out. So it has it kind of like knows something about all the lakes, and it knows it has some previous information about what is likely to be good. Yeah.
If this was a reinforcement learning
Well, yeah, so exactly. So you have to, you as the Netflix engineer get to decide what is the reward. And I just said, in the original problem I said a reward is fish, right? You want to maximize fish. That's when I told you the rewards, when I said what are we maximizing. So for a Netflix engineer, I think it's not clear what your thing is. Like you have to talk to your boss and like figure it out. So in the simple example I gave, it's a click. But maybe people clicking on it and then leaving after 5 minutes is not good. Like maybe we want to maximize how many minutes they spend. Maybe we want to maximize how many friends they tell about Netflix. Like it's up to you as the human to decide what is the reward. But once you decide what the reward is, then it's the same as the weight. You decide what is a fish, and then it's the same as the fishing problem. Okay, yeah, great point. And I think this is like really underrated, right? Like in all these math problems, just someone just comes along and tells you what the rewards are. In real life, deciding what they should be is actually maybe most of the work. I don't know. Okay, so that's one example. And the example I want to get to later in the course that we're trying to aim the end of the course at is AI for games. So, and we talked about this a little bit sort of in the context of like SARSA or Q-learning or something, doing epsilon greedy, trying to choose better. But even more specifically, in a game like chess, you can imagine you have a certain position. Here I have the opening position for chess, and there's all the possible moves that could come from that position. And in games like that we've been doing, like Pig and like dice games, we don't think very hard about the positions. We have a value function. We just look up how much is that position worth. But in a game like chess, it's actually useful to have your computer not just make a move and say like, oh, the value is 7, but actually spend some time analyzing the position. And you can think of the time that you have to analyze the position as a sort of resource that you can use up. And you can decide which of these moves you want to spend your resource on. So imagine your computer has a clock, it has 1 minute to think, and it's going to spend its time thinking about these moves. Now, you could spend all of your time on what you think is the best move, but then if it turns out that move is bad, then you're screwed. So you kind of want to distribute your time between all these moves. And that really does become the same as the lake problem. So instead of having t days to run your computer, imagine you have a computational budget of size t. And here I wrote run t simulations. So imagine that you can sort of think about a position by running a simulation of how the game would go. That's very roughly what we'll be doing. Instead of having L lakes, you have L possible moves you can make. And instead of maximizing the number of fish you get, what we want to do at the end of our T is have an idea of what is the best move. So the rewards are very slightly different. It's not that we want the most number of fish. It's at the end of the fishing trip we want to know which lake is the best. But you saw we kind of did that naturally, right? By the end of the fishing trip, we basically had to figure out it was Lake B, and that is what the computer would do. So that's why we're doing what we're doing now. We're trying to gear up for this algorithm that plays chess or other games really well. Okay, and it is closely related to epsilon greedy and all our other things. Okay. Lastly, the last connection is something called a multi-armed bandit. So imagine you're at a casino. And at a casino, you might see these slot machines. These are called one-armed bandits. And at a slot machine, there's no choice to make. You just pull the slot, and then you get however much money. But in a more complicated octopus casino, there's it's a multi-armed bandit. So you have many slots. And you have to decide which one to pull. So the analogy, instead of having T days of fishing, you have T chances to pull levers. And every time you pull a lever, you have to pull one of the L arms. And instead of maximizing the number of fish, you want to maximize the payout. So imagine that you have a fixed number of times you can play. You want to get the most money out of the machines. This is a stupid example. Why am I telling you this example? This is the official example, stamped, trademarked, official, what people call this problem. So if you Google this problem, you have to Google multi-armed bandit. That will come up. You can do your PhD in multi-armed bandits. You can tell people, I'm an expert at bandits. You go to a conference. What do you study? I study bandits. That's what people call it. I don't know why they came up with this. Clearly, lakes is better. You should have said I'm an expert at lakes. But that's not the world we're in. Okay, so that's why on the game, let's go to the game. On the game, it says best arm. The terminology people use is this multi-armed bandit situation. These are arms. There's 4 arms. And so that's why there's the best arm. Okay. All right, so you have to know that because when we read about it or talk about it, we're gonna do that. Okay, so we played the game already. Now you've had a chance to think about it, and we had a discussion about how you guys went about choosing a strategy. An even simpler question: what is the best strategy? Like what makes the best strategy the best? What is the thing we're optimizing? So in the space of all possible ways you could play that game, what is the thing we're optimizing? What's the objective? And of course, we said it's to get the most fish, right? That's what you're doing. But then you're deciding how to play the game, and you're really optimizing something else. Yeah.
So I guess we're going to optimize learning the distributions as fast as possible.
Okay, yeah, let's write some of these down. Let's write it. So learning the distributions. Okay. As fast as possible. Okay. Anybody have other ideas? Yeah.
Wouldn't we want to optimize the highest average of fish per turn?
So we want to get to by the last turn.
That's our, like,
At the last turn, we want to optimize the highest average. But earlier on, we have this like delicate thing of we want to balance exploring with exploiting. And so how do we do that? Like, what is the way we phrase that mathematically? So basically, what we're going to do, we're going to come up with a math formula for strategies, and we're going to figure out some criteria, and then we're going to optimize the criteria using like calculus. Like, this is why you guys take calculus class. So we're going to make a formula. How good is a certain strategy? And then we're going to, we're going to do the derivative of the formula, and then it's up to 0. Find the best possible strategy. Okay, so this is one thing. I will say, I disagree slightly with this, because learning the distributions as fast as possible makes it seem like we want to know the distribution of each arm. And actually, we don't care about the arms at the side, right? We only care about the best arm. So we need to learn them insofar as we need to decide which one is the best, and we want to make sure we play that one a lot. So learning the distribution, I think, is a little bit asking us too much, right? So how could you phrase like what we're actually trying to do? Yeah.
So I suppose I'd say learning the best distribution as fast as possible.
Yeah, learning the best. I say the distribution of the best arm. Okay, so we don't want, in general, we don't want distributions, we want the best. Just the distribution of the best arm. Okay. I think that's more on the right track. Any other ideas? Okay, here's a question for you guys. Philosophical question. Let's pretend I'm on my fishing trip. Now we know at the end of the fishing trip that Lake B is the best, right? And we know that Lake B gives us on average some pretty good stuff. Let's look at the first day. At the first day, we got 7 fish at Lake B and we got 10 fish at Lake D, right? So on our first day of fishing, Lake D was actually better. Are we at Lake B like kidding ourselves like, oh, we're so dumb, we should have gone to Lake D because you got 10 fish instead of 7 fish? Like, should we be upset on the first day of fishing? Or as the first day we went like fishing at Lake B, like in retrospect, oh, that was a good day. Like we made the right choice. What do you guys think? Is it, what's the actual thing that matters? Yeah.
The average?
The average. And the average, the true average. So even though, we only got 7 on the first day at Lake B, we know on average that Lake B is actually better than the other one. And so we actually would like to go to Lake B, even on days where we don't catch a lot of fish at Lake B, because it's the best thing we can do, right? Lake B has the best average. And so what we really want is to go to Lake B, even on days when we don't catch a lot of fish, because in retrospect, we know Lake B has the highest average. So we're going to make some minor corrections to this idea to make it. So learning the distribution, I say learning which has the highest average. Learning the best arm, the average, the true average of the best arm. So we don't need to know the whole distribution, we just need to know which one has the highest average, and we'd like to go to that one as often as possible. And so we don't even need to learn it, we just need to go to it as much as possible. Go fishing at. Okay, this sentence probably doesn't make any sense anymore. Go fishing at the true average of the best arm. Go fishing at the best arm with the highest true average. Okay, I'm gonna just make a new goal. Go fishing at the arm with the highest true average. So this is, I think, this is like fundamentally what we want to do. And as you've seen before with our gradient descent and loss functions, we need a way to turn this objective into a number, right? So we want to say how close are we to going fishing at the arm with the highest average, turn that into a number, and then maximize or minimize that number. So how do we turn this idea, go fishing at the one with the highest average, how do we turn that into a single number that we can then optimize over? Maybe I'll make some space. We need to make this a number. Yeah.
I mean, it's simple, but we have the average is given to us.
This average.
Yeah, like on each turn, we're given all the 4 averages of all the lights, so we have something to start with there, and then we just need to decide, are we choosing the one with the best average, or are we choosing, if we're using epsilon 3, like you said, we can randomly choose the one with the best.
Okay,
So we'll those.
I think you're on the right track. I just want to make sure one thing, because I think it's an important distinction. When you say average, do you mean this number?
Yes.
Or do you mean the true average, right? And so like on the first day, the average of B was 7 and the average of D was 10. But I want to make sure that whatever I write down still says choosing B is better than D, right? Because B has a higher true average, even though the average of the first day was smaller. And it might be true for some C. So say what you said again.
I mean, we just have something to work off of, but I don't know how to do it for the case, because before, like you said, when we picked one of each, we had an average of 10 in the first one and 7 on B. So
yeah. So I mean, the same. I think the thing you're running into is the same issue we ran into in gradient descent, right? So in gradient descent, we had the true value of the function, and then we had what we thought it was, and we said our score is the difference squared, right? And we want to make that as small as possible. And of course, we don't know the true value, right? So we don't actually know how well we're doing. If we knew exactly how well we were doing, we could figure out the true answer. We don't know the true answer, but nevertheless, we have this idea of the loss, how far away we are, and by writing that down, we can then use it to do things. And it's going to be the same thing here. So I think what you're pointing out is we're not going to know how close we're doing, right? We're just going to have to imagine that there is some distribution and there is some value, which is the expected value of link B. There is some value in the expected value of link D, and we're trying to make some loss function that optimizes choosing link B over and over again. And sort of says choosing link D is worse than choosing link B. And we're going to try to make that as small as possible. And we're trying to think of what it should be. Okay, and before, for like regression, or like matching numbers, it was the difference squared. The difference squared doesn't make sense here. So what are we going to replace the difference squared with? That's the question. Yeah?
Would it be like what we got based on like what we predicted based on the current average for each lake?
Say that one more time.
So like would it be like the difference between like let's say like we went fishing at B, so like
Yeah.
what we actually thought when we went there versus like what we expected to get there based on the average we had beforehand?
I think you're very close. Again, I don't want to rely on the actual numbers, right? Because the actual numbers could be like, even if B is the best choice, we did the right thing by going to B. So even if we get like a bad day of fishing and get a bunch of 4s, I still want us to go to link B. So I don't want us to get a bad score just because we had a bad day of fishing. I want us to get a bad score when we choose the wrong link. Does that make sense?
Mm-hmm.
So I think I want to do exactly what you said, but I want it to be based on not the actual number of fish I caught, but the expected number of fish. So the true value, the true average of each of the links. That's what I would like. Did you have an idea? No, now you're scared?
I want to take it back. I was going to say maybe we could use the standard deviation between all of the averages and that.
So the standard deviation is going to matter because I think what you're on the right track here. So basically this average is not telling you the true average, right? This is the problem. And how far apart is this average from the true average? That has something to do with the standard deviation. So you're thinking the right thing. You're a couple steps ahead of where we are. First, we got to decide what it is we're optimizing, And then we're going to use like standard deviation to analyze what to do. And that's exactly how we're going to get led to the final AI strategy. So you have the right idea, you're just a little early. Yeah?
This might be wrong, but you're optimizing maybe the expected value based on what you got beforehand.
Okay, yeah. So this. I think this is very cool. So our score, or the thing we're optimizing. Let's not say score. The thing we're optimizing. It has something to do with the expected value of the late. Let's call. I'm going to call them x. Choice. So the expected value of where we chose to go, that has some true expected value. Of course, we don't know what it is, but you want to go to the one that has the highest value. Okay? So that's what we're going to do. And the simple way to express this is something which is called the regret. Let me go to the regret. So here's the idea. We're going to think of how much we regret our decisions. Every time we go to Lake B, if Lake B turned out to be the best thing, 0 regret. That was the best choice. We couldn't have done any better. So when we go to a certain lake, the regret is how far away is the average of that lake compared to the best possible average. And so that's the difference, the expected value of the choice. And people usually express it the other way. The expected value of the best choice, minus the expected value of the choice, we know. This is your regret. The regret. Right? This is like you choose to go to a movie, and then at the end of the movie, you're like, well, I chose to go to this movie based on what I knew. It turned out to be a crappy movie. Then you regret it, right? So it's the same kind of situation. And it's really important here that it's based on the expected value. So even if you go fishing, if you went to the best possible lake and you had a bad fishing day, I don't have any regrets about that. I made the best choice. So the regret is just the expected value. And we're going to write this like this. Mu star is optimal, so the best average minus the average we chose. And I think I use A to decide our choices. So this is the regret of choosing A. Choosing A. Okay. Yeah.
By best choice, you mean like an air quotes best choice, like best choice as we see right now.
No, I mean in retrospect, at the end of the game, pretend somebody tells you what the answers were.
I see.
So it's the best one when you have information which you don't have, which is the best information coming from the point of view of somebody who programmed the game, who knows all the rules. It's exactly the same thing we did with the loss function, right? In the loss function, we said our loss is how far away we are from the true value squared. We never know the true value, but if we did, that's deciding what our loss function is, and we built everything based on that. Okay. So this is the regret. And you'll notice the regret is a non-random number, right? The regret is some fixed number. In the example I gave you, so B was the best one. Over here it says the average advantage was 1. And that means that the regret of arms A, C, and D is always 1. Every time you choose A, C, or D, you have a regret of 1. If you choose B, you got a regret of 0. And so the best possible algorithm is not the one that really optimizes the number of fish you get. Like the AI had 343 fish, we had 338 fish. The actual thing is how many times did you choose something other than B? And you pick up a regret of 1 when you make a non-B choice. So our total regret was 4 plus 3 plus 9, 16. We had a regret of 16. On our 40-day fishing trip, we had 16 days where we had a regret of 1. The AI did better than us because their regret was only 12. 4 plus 2 plus 6. So they only had 12 days where they had a regret of 1. Okay, and of course in real life you don't know the regret. This is like a little made-up example where I'm telling you the regret for the purpose of illustration. Yeah?
So just to make sure I know what's going on, we basically recast the problem from get the highest number of fish to get the lowest regret. And those are the same answers, so we're okay, right?
So we're doing the meta problem. So the actual problem is get the highest number of fish. But right now we're trying to come up with the algorithm. And the algorithm should pick something with the lowest regret. So even though on an individual fishing trip, you want to get the most number of fish, when you're thinking about going fishing, you want to have a strategy that minimizes your regret. That's exactly right. Yeah. So that's true. We're changing the levels that we're living in. Okay, so that's the regret. And you can imagine, like in this case, they're all equal. A, C, and D were all 1. But maybe there's some like Lake E that's terrible. It's like a bog, and there's like no fish, and you just like gross. Like you have a lot of regret when you go to Lake D, and you don't fish in it, or Lake E. So the regret doesn't have to be constant. It's the difference between the best and the one you chose. And it's not random. Not random. This is important. Not random. Okay. So what is our job? Our job is to come up with an algorithm that makes choices in a way that makes our regret as small as possible. Yeah.
Wait, sorry, question. So when we say it's not random, like if the action that's like best is random, like is it still not random?
Right. I think you should think about it as you're told exactly the actual distributions after the game. Someone will tell you the actual things, and then you can compute your regret.
Okay.
So the regret is something that depends on the distributions of all the lakes. And if you knew the distributions of all the lakes, of course, there's no point in playing this game. So it's something, if you know the distributions of all the lakes, you can calculate the regret, and at that point, it's not random. It doesn't depend on the random draws. Right? Yeah. Okay. So the regret is not random, and we're trying to minimize it. But of course, we don't have access to the distribution. We don't know the regret. What do we have access to? We have access to the actual numbers we got. We don't even see these averages. So our job is to come up with an algorithm that makes the regret as small as possible. But any algorithm we have is going to be random because it has random inputs, right? So no matter the smartest algorithm in the world, if on our 40-day fishing trip, Lake D was always better than Lake B, it's not our fault, right? Like, we got screwed. Even though Lake B was better, on the 40 days of the fishing trip, Lake D, maybe by some crazy chance, always works out better than Lake B. Lake B has a bad month. And that's not our fault. So our job is not going to be to minimize this, but it's going to be to find an algorithm, and the algorithm has to be random because it has random inputs, an algorithm that minimizes the expected value. So it's random. Okay, so this is the total regret. Our job is to minimize the expected total regret. So our algorithm does something random because it has random inputs, and we want to minimize the expected total regret. And you can write the expected total regret in 2 ways. So the expected total regret. Total regret. So you can write it in one way, which is it's the expected value of the sum of the regrets. So the sum from I, or lowercase t, is 1 to capital T, of the regret you get on day t. That's the first formula. So add up over all the days, what is the expected regret on that day, and how much regret did you get? Another way you can write it, which is equally as well, instead of a sum over the number of days, you can write it as a sum over the arms, over the choices. So this is also the sum from A is 1 to L. So now, instead of summing day by day, we sum lake by lake. How much regret did we get from lake A? How much regret did we get from lake C? How much regret did we get from lake D? And that is what I did a second ago. So instead of adding up over the days and knowing which day I picked like A, C, and D, the only thing that matters is how many times I picked A, how many times I picked C, and how many times I picked D. And this is the second, the more useful formula. The total regret is the expected number of times you choose each lake. So let's say the regret at a certain lake up to time t times the amount of regret in that lake. And the amount of regret in that lake is this constant, mu star minus mu a. So in our case, we picked A 4 times, C 3 times, and D 9 times. So our regret was 16. And you can imagine if we had played this game again, we would get a different number, right? It only came out to 16 because of the way you guys made choices. Depending on how you make your choices, you'll get different numbers for your regret. If you play it a million times, take the average of that, that is your expected total regret. And we would like to play in a way, we would like to make our decisions in a way to make this as small as possible. Okay? That is the objective function we're going to use. And it is like a loss function. You want to make it as small as possible. And that's what we're going to use. Okay. There's one more notation here. This mu star minus mu a comes up everywhere, so we call it delta A. And delta A is called the gap of arming. It's the gap between, it's called the gap because it's like how different is this arm from the best arm. That's the gap. And here are some more notations we're going to use next time. So some of them we already know. L and T are the number of lakes and the number of days. Mu1 to mu L are the averages of the arms. The average of the best arm is mu star. Delta A is the gap, the difference between an arm and the best thing. NA is the number of times we played it. Average of A is the empirical average that we saw. So this is different than mu. Mu is the true average. Average is what is printed on the computer screen of the days we went there. What is the actual average we saw? Okay, so these are the things we're going to use to analyze. And we're going to start by analyzing really simple algorithms. So like here's a simple algorithm. Pick one arm at random. So I'm feeling lucky. I'm just going to go fishing at Lake C for the full 40 days of the trip. And there's a chance that Lake C is the best lake and then I'll do well. So this picks each arm with probability 1 over L, right? Each of the L arms. So if you want to make sure you're following along, you can try to calculate this on your own. And this is what we're going to pick up next time. We're going to calculate this formula. It's going to be some formula. And we're going to see what the expected total regret is. And we're going to see, can we do better by something more complicated. But yeah, if you want to make sure you're following along, try to do this one yourself. Okay, we'll stop there.